We'll start with the session 2, that is the ultraviolet visible spectroscopy. In the previous session we have learned about what are the principles of the spectroscopy and what are this overview of the spectroscopy. Today we'll start in the section 2, we'll start about the ultraviolet visible absorption spectroscopy. So as the spectroscopies are various types. One among them is the primary, and the one among them is UV visible spectroscopy. What are the principle of a UV visible spectroscopy is nothing but the molecules containing the electrons and non-bonding electrons can absorb the energy in the form of ultraviolet or visible light to excite these electrons to higher anti-bonding molecular orbitals. This excitation phenomena will be analyzed to estimate the concentration of biomolecules present in a given sample. So here, as every molecule has its own absorption wavelength, the molecules which have the capability to absorb light in either the ultraviolet region or the visible region absorbs the light and excites to the higher state. So when this higher state energy was released, they again release some energy in the form of either heat or mechanical energy to get to the ground state. So during this excitation, the amount of light absorbed by these biomolecules can be utilized to calculate the concentration of these biomolecules in that particular solution. Since this is an absorption technique, the observer will perceive the complementary color that has not been observed. As if you are using the colored solution, as they'll be having two different types. One is excitation, the other one is emission. The observer will observe the light which is emitted by the molecules. These are some of the common functional groups which can be absorb light in the UV region or the visible region. So UV visible spectroscopy refers to the absorption spectroscopy which absorbs light in the ultraviolet region or spectral region, which ranges from 180 nanometers to the 720 nanometers. Here the molecules will interact with either the ultraviolet waves or the visible waves. Okay, here the absorption or the reflection in the visible region directly affects the perceived color of the chemicals involved. In this region of electromagnetic spectrum, molecules undergo electronic transitions. This technique is complementary to a fluorescence spectroscopy. With this, about the fluorescence spectroscopy, we'll discuss in the next sessions. What happens exactly in the fluorescence spectroscopy is, here in the fluorescence spectroscopy, we'll add a fluorescence molecules which excites after absorbing a light of particular wavelength, and while reaching to the ground state, they emit energy and emits this energy in a next region, and that is it emits the light of other wavelength other than the absorbed wavelength. So what is actually being observed spectroscopically is the absorbance of the light energy or the electromagnetic radiation which excites electrons from the ground state to the first singlet excited state of the compound or material. So what are the main components of this UV visible spectroscopy are? First one is the source of the light, sample containers, monochromators and detectors. Let's discuss about one by one. So what is meant by this source? So to provide the light of different wavelengths, we need a light source. So the light sources can be a lamp which emits all colors or a particular wavelength. Monochromator, and next one is the monochromator. If we are using the lamp or the light source which emits all the colors, so we need a monochromator to select particular wavelength according to the absorption of the absorbing molecules, such that it selects a particular wavelength and incidents that wavelength of light to the molecules. Next one is detector. So now here the detector will detect the wavelength of the light that has passed through the sample. And next one is amplifier. Here the amplifier increases the signal so that it is easier to read against the background noise. Apart from these components, there are again three types of spectrophotometer. One is single beam, double beam and simultaneous spectrophotometer. Among all of these instruments, all of these instruments have the same light source, a sample holder, a monochromator and a detector and analyzer. But what it differs is, in a single beam instrument, this instrument has a filter or a monochromator between the source and a sample to analyze only one wavelength at a time. It means this single beam instrument uses a monochromator between the light source, and that is the source and the sample, such that to pass through only a single wavelength of light. In the double beam instrument, this has a single source and a monochromator, and then there is a splitter and a series of mirrors to get the beam to a reference sample and the analyte sample to be analyzed. So the main here in the single beam, we'll have to analyze the sample one after the other, whether it is a reference sample or the analyte. But in the double beam instrument, here we have two beams, two holders. That means we can analyze reference sample and the analyte sample simultaneously. In contrast, the simultaneous instrument does not have a monochromator between the sample and source. Instead, it has a diode array detector that allows the instrument to simultaneously detect the absorbance at all wavelengths. It means we can detect or analyze the sample at all the wavelengths simultaneously because of the presence of diode array detector. It is much more faster and more efficient, such that we can have the absorbance or calculate the absorbance at various wavelengths at a time. So these are the difference between the single beam, double beam and simultaneous measurement. So let's go to what are the advantages as well as the applications of UV visible for spectrophotometer. So the foremost application of the UV visible spectrophotometer is to determine the qualitative and qualitative information of a given compound or a molecule. Irrespective of whether quantitative or qualitative information is required, it is important to use a reference cell to zero the instrument for the solvent. It means if you to cut short the adsorbance of the solvent against the solute, we need to take the information, or we need to calculate the absorbance of the solvent sample, and we need to set it to a zero to reduce the background noise. For quantitative information, calibrating the instrument using known concentrations of the compound in question in a solution with the same solvent as the unknown sample would be required. The information needed is just proof that, however, it means if it is a just qualitative, we need to determine only the calibration curve. To make a calibration curve, at least 3 concentrations of the compound will be needed, but 5 concentrations would be most ideal for a more accurate curve. The concentrations should start at just above the estimated concentration of the unknown sample and should go down to the above an order of the magnitude lower than the highest concentration. The calibration curves should be spaced relatively equal apart, and they should be made as accurately as possible during distal pipettes and volumetric flasks instead of graduated cylinders and beakers. So these are some of the further and advanced applications of the UV visible spectrophotometer, that is detection of a particular functional group. See, every functional group has a absorption wavelength of its particular according to its wavelength. They absorb the light at a particular wavelength. So within the region from 180 to 780 nanometers, every functional group has its own absorption wavelength. So utilizing this functionality, we can calculate or we can determine the concentration of that particular functional groups in that particular solution. The other one is the extension of conjugation. For example, if we are conjugating any molecules on the surface of the other molecules, we can also determine the concentration, or we can determine